All right. In this module, we're going to move on to electrostatics. Traditionally, when you take a physics sequence in a physics department, you'll take physics one and physics two. Physics one is pretty much everything we've talked about so far, leading up to this point. So all the mechanics and the heat, thermodynamics, usually all that is in physics one. So now we're sort of moving into physics two material, which is like electrostatics, electrodynamics, circuits, electricity, magnetism, that kind of thing. Um, so we'll start with electrostatics, which is essentially just charges that aren't moving, but they do have a charge, so they attract and repel things around them. The four topics we'll cover this time in this first lecture is essentially just quickly discussing where these ideas came from. So Benjamin Franklin, who was a big contributor to the ideas that we still use today. We've got electric forces, so the fundamental attractions, just sort of like gravitation, fundamental attractions between two objects that are charged. And then we'll talk about where those charges come from in the atom, and then conservation of charge is another topic we'll hit. And then one more I've not got on here, but it will be Coulomb's law. So Benjamin Franklin, he was, well, you all know this, he's very popular. He was an inventor of lots of things. The lightning rod, the glass harmonica, the Franklin stove, the bifocal eyeglasses, even the flexible catheter. Um, he's also sort of bifocal or known to have flown a kite in a thunderstorm. He didn't actually fly it during a thunderstorm, he flew it before a thunderstorm, but actually determined that what was the cause of lightning was actually electricity. At the time, electricity was thought to be essentially two types of fluids. And then building off of that, Franklin determined that maybe we should differentiate between these two as positive and negative. And if you're interested, there's a lot more information on Benjamin Franklin. As you can see from this link here, it's got the Franklin Institute has a whole list of things he's developed. His lightning rod experiments pretty much showed that metals with a sharp point, and that sharp point part is useful to remember. That's special, we'll get to that later. But the sharp point could collect or discharge electricity silently, preventing charge buildup on buildings when there's like a lightning storm or clouds are being charged overhead. So essentially, if you had your building, basically a long, skinny rod would sort of discharge clouds into the rod instead of discharging into the house, setting the house on fire. On his own roof, he actually installed several rods. He was also a proponent of installing them on a couple of different federal and governmental buildings. One of those is University of Pennsylvania now, and then I think the other one is Independence Hall. So he was a proponent of putting these lightning rods on important buildings. Essentially, how he described it was these rods will actually draw electrical fire, is what he called it, silently from the clouds before it struck as lightning. So the term we use is very broad. Just electricity is the general term we give to all things electric, kind of like how gravity is just that catch-all term for any sort of gravitational thing happening. Sometimes we'll call G gravity. But really it's the acceleration due to gravity. ACC due to gravity. So it's kind of the same thing. We lump a lot of things into the term electricity. And of course, you can find electricity pretty much anywhere in everyday life. You've got lightning. When you strike a match, that spark, that's an electrical phenomenon. It's a thing that holds atoms and molecules together. And every time you turn on a light switch or pick up your smartphone or any other everyday device, you're pretty much interacting with electricity. So that's why when you do your traditional physics sequence, physics 2 is sort of mostly dedicated to the concept of electricity and magnetism, because just like mechanics, where it's just the movement of everyday things, this is sort of looking at the movement of electrical currents through everyday things. But what we're going to talk about first is essentially the idea of electrostatics, which is energy and electricity at rest. So charges are sitting there, they have an electrical force on them, but the charges themselves are not moving. Moving charges get more complicated. So broadly put, the way the book sort of motivates this is like a big supposition. Suppose that, suppose that, suppose that. So we're gonna think about it kind of like that, but not as big and broad and touchy-feely. But instead of saying suppose that, we're just going to assume that there are two types of particles in the universe. There's lots of particles in the universe, but two particular ones. They could consist of charges, so positive or negative charges. Positive charges repel positive charges. So having two positives together, they repel each other. But positives will attract negatives. So these two want to repel, but if they are opposite, they will attract. Same thing, negatives repel negatives. These two want to move away from each other, but a negative will attract a positive. Okay. So this force, this weird mystery force, I'll label it, this force interacting between these particles, this is the electrical force. We can see a visualization of pretty much what I've said here. You can see these two rods hanging. So these two rods, because of gravity, want to hang straight down, but you can see something is pushing them apart. And that's because they have similar charges on each side. Same thing here. In both cases, these are like or similar charges. So they're going to repel each other. But if you have opposite charges, they will attract and actually come together. Now, the question is, what causes that? And we can talk about that here. So inside every piece of matter are atoms. We sort of hinted at that in the last section, the last module on thermodynamics, and heat, where we have energy transfer through molecular collisions. But if we take those molecules and break them down even further, we have individual atoms. Inside every atom are positive and negative charges, and they are held together by the attraction of the electrical force. Okay, so by forming compact and evenly mixed clusters of positives and negatives, the electrical forces balance themselves out almost perfectly. So for how much ever positive you have in an atom, usually, you're going to have roughly the same amount of negative, and they're essentially going to roughly balance each other out. When two or more atoms do join together to form a molecule, so you can think of like a water molecule, an H2O molecule, so two hydrogens, one oxygen. So Generally, the molecule also contains balanced positives and negatives. Something that we'll talk about later is actually those balanced positive and negatives could be in slightly different places. You can think about the positive up here, negative down here. I can't remember which way is which, but nonetheless, with a water molecule, it's actually a polar molecule. So even though you've got sort of a positive negative thing going on, you can actually have them in different places. So you sort of have some positive over here, some negative over here. So there could be some slight charge separation. But usually you're going to have a balance even after things combine. So the terms positive and negative refer to electrical charge, as I'm sure you know just from intuition. So these are the fundamental quantity. This is the fundamental quantity that underlies all electrical phenomena. So we have some fundamental charge that could be positive and some fundamental charge that could be negative. And we'll talk about what that value is in a little bit. So the positively charged particles inside the nucleus, they're the protons. And you can find them in here in the nucleus. The negatively charged particles, those are electrons, and they actually orbit outside. So you'll notice that in this next statement, I say the proton is in the nucleus of the atom, and the electron circulates outside. If we get time and we get to some quantum mechanics, what you'll find out is the electron does really weird things. It moves in really weird ways outside of the nucleus. What we usually do is we just simplify it and just draw it as an orbit. But in reality, it does crazy stuff. So that's why I said it circulates outside. Usually, well, no, you'll always find electrons outside. You'll find protons inside of the nucleus. And then, of course, you see these neutral things in here, and those are actually neutrons. They have no charge. They're a very similar mass to protons, but they just sort of hang out and give the nucleus extra mass. So what happens is because of the way that these electrons move around outside, sometimes that'll set up a charge imbalance, which is just due to the movement of electrons. And that charge imbalance will actually cause atoms to start becoming attracted and forming molecules. Let's see. So here's just essentially a summary of what we just talked about. So I can run through this quickly. Every atom is composed of a positive nucleus surrounded by negative electrons. The electrons are all identical. Okay, so all of these electrons, so we have one electron here, we have another electron here. They all have the same charge. So the way we could simplify this is just by saying all, now this is a fundamental charge. They all have the same charge. We don't know what the number is, but we're just going to call it E negative. All electrons, you can write an electron in shorthand, so to speak, all electrons have the same charge. So they all share the same value. They're all equally charged. Protons and neutrons make a nucleus. Protons are way more massive than electrons. And you can kind of see that in this image. You can see are larger than the electrons. Protons are huge. Electrons are actually tiny. But they carry an equal charge as the electron, but it's a different sign. So protons, so all protons, so we can abbreviate that as E positive. So you can have something that's negatively charged. You can think about it like a sink, it's a negative value, or we can have something positively charged. Electrons and protons, they have the same number, it's just one of them is positive and one of them is negative. So all protons have the same charge. Atoms usually have the same number of electrons and protons. You can see here, you've got 2 protons and 2 electrons. There we go. And when you have 2 of the same thing with a positive and 2 of the same thing with a negative, they cancel each other out. So the whole idea here is you get net charge. So essentially 2 protons plus 2 electrons equals 0 charge. Now, we've talked about these charges and where they live, so to speak. So now we need to talk about, check one thing. Okay, so now we need to talk about new idea of constant charge. So just like conservation of momentum, conservation of energy, first law of thermodynamics, second law of thermodynamics that sort of build on that foundation. It doesn't have a conservation of charge. So what that means is essentially electrons cannot be created or destroyed. They're essentially a fundamental part. Since they can't be created or destroyed, when you charge something up, like with static electricity, that just means you're moving electrons around. They're simply transferred from one material to another. And this is the whole idea behind conservation of charge. Now, when it happens, if we have atoms and we move or we add electrons, then we get an imbalance, right? Because remember I said atoms usually have the same number of protons and electrons, but if we start messing with that, we make something called an ion. So in a neutral atom, the number of protons and neutrons are usually equal, so there's no net charge. But if you remove electrons, okay, so if you get more, if you have 2 and 2, but if you remove an electron, then you get more positive than negative. Okay, so the removal of these electrons creates a positive ion. So then it would have a net positive charge. If you add extra electrons, so if you had 2 protons in the nucleus, but then for whatever reason you see like 5 electrons in the atom, well, that would be more negative than positive. So you would create a negative ion, so it would have net negative charge. All right. So we've talked about charges, talked about atoms. Let's see, charges, atoms, we talked about the protons, the neutrons. So we know that they attract each other, but can we calculate by how much they attract each other? Or we know that they could repel each other. Can we calculate by how much they repel each other? So just like the gravitational force, the electrical force decreases inversely as the square of the distance between bodies. Okay, and we'll talk about that in just a second, what that means. But for now, just be prepared to talk about Coulomb's law. Okay, so we have Coulomb's law. And Coulomb's law in words pretty much states that for 2 charged objects that are much smaller than the distance between them, okay, so 2 objects that are much smaller, so these are tiny compared to some distance between them, okay? In this case, the force between the 2 objects varies directly as the product of their charges and inversely as the square separation distance. That sounds like a lot, but if we just look at if the same statement in word form, what you see is essentially you have the product of their charges, okay? So we have a Q1, and that's usually how we represent a charge as Q. So we have Q1, Q2, Okay, so it's the product of their charges. So that's the numerator. Okay. Then this changes inversely, right? So remember, inversely means a 1 over x kind of thing, right? So it's inversely as the square of their separation distance. Square of the separation distance. Well, that's the denominator. So really, what the separation distance is, that's right there. That's r. That's just the distance between two charged objects. Okay. Now, if that's confusing, don't worry. We'll get into it a little bit more here shortly. So if that was a lot, then we can talk about the inverse square law sort of in with pictures. So as you know, the further away from the Earth you go, the strength of gravity drops off. That's why eventually things are weightless, right? People floating around in the International Space Station, they don't feel any gravity. That's because they're really far away from the Earth. So you can imagine if we look at this first image, they may be, I don't know, up here, right? Really far away. And you can see that gravity gets weaker and weaker and weaker as you move away from the Earth. Okay, so this is the inverse square law. This curve right here is just 1 over r squared, essentially. So just like with the charges we just talked about, if you want to calculate the force of gravity between like two objects in space, well, it turns out it's almost the same thing. You have the two masses, m1 and m2, and then it drops off inversely due to the distance between them. That's where the r squared comes in down here. This is different because the big G deals with gravity. Our other letter here, K, that deals with electrical stuff. We'll talk about what those are in just a second. But just realize that the math for gravity and electrical charges, when you're looking at two things attracting, or in the case of electricity or charged objects, attracting or repelling, the mathematics is the same. And you can think about this inverse square law as like a puff of paint from a paint can. So you can see we have a paint can here. And if you spray it once, okay, and then you go out some distance, you're going to get a big glob of paint, right? Because it's really close to the can. But as that puff travels, it covers more and more area. And it gets that same amount. We're not adding more paint. We're just taking the same amount and spreading it over more and more area. So by the time you get to here, it's just like a thin mist of paint that's going to cover something. So the whole idea here is essentially as you move away from something, whether it's with a gravitational force or an electrical force, the further away you get, the more that force has to spread out and cover more stuff, so to speak. Just like this can of spray paint, as the puff leaves, it spreads out, gets more thin. It's the same amount, but because it's decaying as a 1 over r squared, it's going to spread out more and get thinner because it's having to cover more area. All right. Let's go back to Coulomb's law and review this again. So again, r is the radial distance between the charged particles. So instead of the typical x, we're just going to replace it with r. So we can replace this x with an r. That's just the distance between two particles. And it's squared. That's this term here. Now we have the charge on the two particles. So this one looks like it's negative 4q. We don't know what q is yet. That's totally fine. This one's positive 2q. So we have two differences here. We have a negative 1, so probably made up by electrons. We have positive 1 made up by protons. Okay. So the first one, q1 is the charge of one particle. So that's going to be negative 4q. Q2 is going to be positive 2q. And then K is essentially just a proportionality constant here. Okay. Now the value for K is actually really big, and that's fine. The K is just something that never changes. It's kind of like pi or E, like when you raise E to the something. Or we could even say it's kind of like the number 12. The number 12 is always 12. So it's just always a constant. It's not going to change at all. So there's the definition of everything in the formula. The next thing we need to talk about are the units. So when we actually measure what Q1 and Q2 are, so these are actually going to be measured in coulombs. That's how we measure how charged something is. So this is let me change back to green. So this is a coulomb, and this is a coulomb. It's negative 4Q coulombs plus 2Q coulombs. We still don't know what Q is, it doesn't matter. But that's just the SI unit. Of course, when we multiply all of this out, what the end result is still going to be newtons, right? Because it is a force. But we have to take in distance in meters, charge in coulombs, and then this constant, right? And when we put all that together, our output is going to be in newtons. So the value of the proportionality constant, K, is very large. Okay, so that's something to think about. With gravity, if we go back and look at G, G is actually really small. But K is very big. We're talking 9 times 10 to the 9th Newton meter squared per Coulomb squared. Okay, so now we can actually talk about what Q is. So it turns out that just 1 Coulomb is a huge value. Okay. So if we know that 1 Coulomb is huge, it makes sense when we look at the values of the charges of protons and electrons. So a proton, which is the fundamental positive charge, is plus 1.6 times 10 to the negative 19th. That's 1.6 with essentially like 19 zeros in front of it. It's tiny. So this is 1.6 times 10 to the negative 19th coulombs. Okay, so that's how weakly it's charged. An electron is the negative of that same number. So an electron is negative 1.6 times 10 to the negative 19th. So you can imagine if you had like a trillion protons or electrons, then you start getting closer to 1 coulomb. So just think about that. If these are that small, how many does it take to actually make 1 coulomb of charge? So 1 coulomb by itself is a massive amount. And again, we abbreviate these as just E positive, E negative. So that fundamental charge that we've been talking about, and I've been avoiding the value of, we could say a fundamental charge Q. In this case, Q is just a charge of anything, right? So we could say like, oh, Q equals 2 coulombs on something, but in this case here in this problem, we could say as an example, okay, Q equals maybe 1 1 proton. So that would be 1.6 times 10 to the negative 19th coulombs. We could also say something like Q equals 2 E negative. So that would be 2 electrons. So it would be 2 times negative 1.6 times 10 to the negative 19th C. So the whole idea is essentially taking this big number, let's see, taking this big number and just rewriting it. So you'll notice this one's negative, since we're talking about electrons. This one's positive since we're talking about protons. Let's bring all of this together in one example here, and then we'll go ahead and call it a day. Okay, so we have two charges. One is of 0.1 C. Now notice that's a small number, right? 1 coulomb is huge, so we're going to be dealing with some pretty small numbers. So we have one particle, one charged object of 0.1 C and one 0.2 C, okay? And they are 0.5 meters apart. So what is the electric force between them? Now, we know that they're going to fly apart, right? Because they're the same. They're both positive. So we know that there's going to be a positive force, a repelling force between them. But now let's calculate how much that is, how strong that is. And we can do that with our equation we've been using. Okay, so we know that the charges Q1, Q2, we have those. So we know what Q1 is, we know what Q2 is, right? We can plug those in right here, Q1, Q2. Now we know what the distance is as well. It's R equals 0.5 meters. That goes in our denominator and it's squared. All right. Now remember, K just comes along for the ride. That's K. We just bring it with us. Now you need to be good at scientific notation in your calculator, or you can use Wolfram Alpha. It's just Wolfram Alpha.com. Imagine Google, but for typing in math and doing math. So make sure you set this up correctly, and then you can just type this in Wolfram Alpha and it'll give you an answer. So it turns out the repelling force between these two particles is 7.2 times 10 to the 8th newtons. I went ahead and wrote it in scientific notation, so it'd be easier to say. This is really big. Okay, so far we have never dealt with a force this large. So you should really think about that. Some of the largest forces that you're ever going to deal with, at least in this course, are actually from the tiniest things, the tiniest particles like protons and electrons. You can get some incredibly large forces between these two really small things. So that was essentially just a quick introduction to charged particles, electrons and protons, where they live in atoms, and how we can calculate the forces between them. So again, we do that with Coulomb's law. All right. And with that, we'll stop. The next time we'll actually talk about how we can store these charges and how we can store things like electrons on certain materials. And then once we figure out how to get these things stored on certain materials, we will talk about actually using these to move them and actually get electrons from one place to another and start creating currents and circuits and things like that.